So hello there and welcome to another tutorial. My name is Henry Bakshi and this time we're going to be going over Tower of Hanoi Part 3. Now, just in case you haven't watched the other parts and you wanted to skip straight to 3, here's a little rundown or a recap of the other parts. Now, it's been quite a while since I've released Part 2 or even Part 1, so here it is. In Part 1, we covered what the Tower of Hanoi is, because as I know, it's not that much of a famous game, so some people don't know about it. So we talked about what the Tower of Hanoi is, we talked about how you can play the Tower of Hanoi, all the rules, etc. And then we talked about how many minimum number of moves it would take to actually solve optimally one Tower of Hanoi game with n number of discs. Then, in the second part of our tutorial series, we went through the algorithm that I created, and it uses the trees data structure. Now, I'm not exactly sure, and I haven't actually seen this online yet, or in any book or anything, so if you can find it, leave it in the description, or, in the comments, or you can email me at tadgman@gmail.com. More info on that at the end of this video. Anyway, then we talked about solving the puzzle manually, and we also talked about the code itself. So I showed you the code, I showed you an implementation of it in Swift 2, and so now in this part we're going to be showing you the UI for this code. Now, I'm not going to be making an entire sprite kit full-fledged UI or even a scene kit full-fledged 3D UI. All that I'm going to be doing is I'm going to be creating a character user interface for you, meaning it'll print out turn this of this, moving this disk from peg this to peg that, and then it'll be like those old DOS or command line sort of printed graphics. So it's gonna be fun, yeah. Okay, so let's get to the Mac part now, where I'm going to be demonstrating how to create the character user interface for the Tower of Hanoi. Let's get to it. So welcome back to the Mac part, and now I'm going to be showing you the code of this app, and also before we get into the code, I'm going to show you a little demo of this app. So let's just make my face smaller and move it to the corner here. Now I'm going to make this full screen and move it out of the way a bit. Okay, perfect. Now let's just see how many disks we want to give an example of. So first of all, I'm going to give an example for 3 disks. So if I type in the number 3 here, and I click enter, as you can see, it gives us this wonderful little character user interface, and it says turn 0 of 7. So it calculates the number of moves that it will take, and then it sees which move we are currently on. And then we use a print legs function to actually print out these legs over here. Next, we can just click enter, and as you can see, turn 1 of 7, moving disk 1 from peg 1 to peg 3. Turn 2 of 7, moving disk 2 from peg 1 to peg 2. Now, as you can see, this will continue. It's on turn 5 now. Now it's on turn 6. And as you can see, it has solved it. Now if I click enter, we'll just stop. Okay, so that was an example of 3 disks. Now, just before we get into the code, I'll show you an example of 4 disks, then we'll get to the code. So 4 disks, turn 0, 14. And as you can see, as I click enter, this Tower of Hanoi puzzle is getting progressively solved. And turn 14 and turn 15. Perfect. Okay, now what we're going to be doing is we're going to go into the code. So now let's close this down and let's do this. Okay, so now I'm also going to show you a demo of 5. However, first I'm going to go through the code, then I'm going to show you 2 more demos. So, okay, perfect. Let's get started. Now, there is some code that you should already know from the older parts, such as this Hanoi node class, which holds the disks, the from, using to, leaf 1, leaf 2, leaf 3, and the initializer. So you know that from part 2. Now there's one thing that you don't, yes, you do know this, the inst array. It's an array of strings which holds our instructions. Then there's this input function, which I did not make this. I got this from somebody's blog. I forgot the name. I will leave the link in the description. Okay, so this is an input function. What this allows us to do is it allows the user to enter input. In this case, I'm just using it to have the user enter, or actually just click the enter button so I know when to move to the next turn. Okay, then there's a function that you haven't exactly seen before, the Hanoi function. What this function will do, or actually the Hanoi underscore function, is it takes disks as an integer. It takes A as an integer, it takes B as an integer, I mean A is a string, B is a string, and C is a string. So disks is the number of disks that we're going to be using for this Hanoi puzzle. Then A is going to be the name of the A peg, then the name of the B peg, and then the name of the C peg, of course. Then you know already all of this code from part 2 again. These are the contents over here where we declare the initial leaf or node. Then we check if it has leaf 1, and then we check if it has a leaf 2, and then we check if it has a leaf 3, etc., etc. And then so we go on from there. Okay, perfect. So next, after the Hanoi underscore function, we have the normal Hanoi function. Now this has a function much more similar to what a user would want. This just takes disks. That's it, nothing else, and it returns an array of strings. And so the array of strings that it returns will be the instructions required to actually solve the Hanoi puzzle for the required amount of disks. And this function just calls the Hanoi underscore function with the disks that you gave it. The A peg named as A, the B peg named as B, and the C peg named as C. And then we just return inst or the instructions array. Perfect. Then we have a new function which you haven't even heard of before. It's called printlegs. What this does is it takes disks as an integer. These are how many disks we're going to have in the legs. Then it takes var a as the entire peg, not just the name of the peg, the actual contents of the peg. So if peg A, if we're just starting out, then peg A will have all the disks in the container. Let's say we're starting out with 3 disks. A will be 1, 2, 3, B will be blank, C will be blank, etc., etc. Okay, then what we're doing is we're checking if a.count is less than disks, meaning not all of the disks are in A. If so, then go for I in 1 to disks minus a.count. What this will do is it'll see how many disks are not in A. Depending on how many there are, loop through that many and insert zeros in their place. So instead of having something like this, let's just imagine this is A, 1, 2, or sorry, this is A, 1, 2, over here. Then this is B, which is just a 3, and this is C, a 4. Now, instead of having A as 1, 2, we're going to have it as 0, 0, 1, 2. Then instead of having B as just 3, we're going to have it as 0, 0, 0, 3. And instead of having C as just 4, we're going to have it as 0, 0, 0, 4. Because there are 4, as you can see, disks that we could have put on this peg. There are 3 of them, and so we add 3 zeros to make up for those places. Okay, then we do the same thing for B and C. Then we loop through for I and 1 to disks. So what we're going to do here is we're going to say print and then, listen carefully because this can get a little bit complicated. We're going to print pipe space, then the A peg array, I minus 1. So we're going to say which disk are we on. Okay, if it's, let's say we're on the first disk, we're on 1. We're going to say 1 minus 1, that's 0. So we're going to get the 0th element from A. When we get the 0th element for A, we put it in between these pipes, and then we have 4 spaces, and then another thing, except instead of A for B, then 4 spaces again, and then for C. Then what we're doing is we're handling what happens if we have a 0, or if we have, since we've inserted all the zeros. Now, before I even continue, what I'm going to do is I'm going to quickly take this little snippet of code, Command exit, and put it in a comment here. Now if I run the app, as you can see, I've removed that little line of code. Now if I run the app on, let's say, 3 disks, it shows you all the zeros that we've inserted into peg A, peg B, and peg C. So instead of just having nothing in these pegs that are blank, it has 3 zeros. So now if I click enter, it's 0, 2, 3, 0, 0, 0, and 0, 0, 1. And as you can see, it keeps going on. So the arrays of the pegs are actually never empty. They're always full of something, like completely full to the brim of at least normal disks or zeros. But they will be completely full, because then what we're doing is this command that I removed actually replaces all zeros with spaces from inside of that string. And so what happens is if I run this now, as you can see, all the zeros that were in these pegs have been replaced with spaces. And so we don't see the zeros. So it's programming friendly and it's user friendly as well. Perfect. Then all we're doing is we are just printing out 5 equals, then I think 1, 2, 3, 4, yeah, 4 spaces, then 5 equal signs, then 4 spaces, then 5 equal signs, then a new line, and then print adds a new line by itself. This is so that we have this little ending of the jar here. It's like a little illusion. It's like the equals act as the bottom of the jar. Okay, then we're just printing, so it adds yet another line. Okay, actually, instead of doing that, we could just do this. Perfect. Okay. Next, we're getting into the really, really interesting stuff. So let's just close that so you can see the code nicely. Okay, so now what we're doing is we are creating a new constant called ndisk. Now, ndisk is the variable that will hold the number of disks that we have throughout the game. And so in order to calculate this, not really calculate, you get the input by doing the integer conversion of the input function that I just introduced to you a little while ago, and then we are force unwrapping this because I don't want to implement error handling yet. This is just a proof of concept for simple programming beginners. Not beginners, but you get the point. Just the Tower of Hanoi, and so I'm expecting that the user has inputted a number. So you can take care of the error handling if you'd like to, or you can email me if you need assistance with that. Anyway, after that we are creating the pegs dictionary, which is a dictionary of index type string and value type array of integers, and we're declaring this as a blank dictionary. Then what we're doing is we are doing a loop for I in 1 to ndisk. This is going to loop through from 1 to 3 if we type in 3 numbers or 3 disks, 1 to 4 if we type in 4 disks, 1 to 5 if we type in 5 disks, 1 to etc. You get the point. Okay. So next we are creating a actually, sorry, I forgot to tell you. Inside of this loop, what we're doing is we're checking if I is 1. If I is 1, we are setting pegs A to a blank array, pegs B to a blank array, and pegs C to a blank array. And then what we're doing is, regardless of if I is 1, or if it's 2, or if it's 3, or if it's 4, whatever, we are just saying pegs A dot append I. That's simple. So what it's doing is it's saying fill up A with the amount of disks that the user gave us. So if he gave us 3, fill up peg A with 1, 2, 3. If he gave us 10, or actually 10 doesn't work with this app, 9, then fill it up with 1, 2, 3, 4, 5, 6, 7, 8, 9. That's simple. Okay. Then we have a new constant outside of this loop, and what it does is this is the total turns that our app will need to create, that our app will need to take. And so we calculate this by taking the power, 2 to the power specifically, 2 to the power ndisk, then we minus 1 from that, and then we convert that to an integer. I believe we can force unwrap that. Okay, never mind. Only converting strings to integers gives you an optional. If you convert a double to an integer, it does not give you an optional, so you don't need to unwrap. Okay, then we just print out turn 0 of total turns. Then we call the printLegs function that we just created on the 3 pegs that we have and the end disk. Then we just take input, meaning we're waiting for the user to click enter, or they can type whatever they'd like at, really. But once they click enter, it will actually start with the actual solving. Okay, then we're actually storing turn as a variable because we have to change this. I can't have this as a constant. Okay, then what we have is we have a function called peg English. So what this does is it takes a peg as a string and it returns a string. Now we expect this peg to be either A, B, or C. So we're doing a switch case on this peg string, and we're checking if it's A, return peg 1, if it's B, return peg 2, and if it's C, return peg 3. The reason we're doing this is, let me just show you. Because as you can see, it says moving disk 1 from peg 1 to peg 3. It's actually peg A to peg C, but then we call the peg English function on these pegs to get peg 1 instead of A so that the user can understand it. So it's a bit more, user friendly. Okay. So if it's not A, B, or C, we just return a blank string because we don't know what this is. Actually, you know what? I don't think Swift 2 requires you to have a default case. Yep, it does. Anyway, okay. Perfect. Or in this specific case, it told me that you have to have a default case. Okay, then we have a very big loop. This is for I in Hanoi end disk. So what this will do is it will call Hanoi function, which will return an array of instructions of how we can solve the Tower of Hanoi. And so we're calling that function with end disk. And so we're looping through the instructions required to solve the Tower of Hanoi for a specified number of disks. And so first of all, what we're doing, this is the most important, we're just incrementing the turn so that the user can see what turn they're on. Then we're actually printing turn of total turns. Then we're seeing, since these, instructions are formatted in this sort of way, like let's say we have to move peg 1 to peg 2, aka in computer language, peg A to peg C, B, then actually what it's giving us, the real instruction from the array, would be A to B. Or, just a sec. No, it's actually, that was an older method of mine. It's actually just AB. So it's a very simple language for the computer to understand because the from is the first letter and the to is the last letter. There can be anything in the middle and the computer will just ignore it. Because all Swift is doing is it's parsing out the first character and parsing out the last character. Okay, perfect. Okay, so now what we're doing is after we've calculated from and to, we are going to print out moving disk. Now, this is a bit hard. We're moving disk pegs from, so we're seeing which peg are we moving from. Take the highest disk in that peg, the first disk in that peg, and replace it here and put it here. So moving disk, then whichever disk is on the top of the peg that we're moving from. Simple. And then we're saying moving this disk from this peg, so peg English for the from peg, to, and then peg English again for the to peg. Simple again. Then we're just making a new line. Okay. It's a bit complicated, but once you just read it a few times, you'll get the point. Anyway, after that what we're doing is we're saying pegs to. So now we're actually moving the disk in software terms. So we're saying pegs to. So we're taking the to peg and we're force unwrapping it, and we are inserting whatever we remove. Actually, we're inserting from the pegs for the from. How do I explain this? if I do this, it could be a bit simpler. From value is equal to this. Now, quick thing I need to tell you first. When you call the remove first function from an array or you call this function on an array, it will remove the first value from the array, but it'll also return that first value to you, so you can use it in, let's say, a variable. And so what we're doing in this case is we're removing the first value from the from peg, because of course we're going to remove from, put on to. So we're removing it from the from, and we're getting that value. We're getting that disk value. And so what we're doing is we're taking that disk value and inserting it to the 0th index, the highest index, the first spot on the to peg. Now it's quite simple. Okay. If you'd like more information on that, or this is essentially simulating a stack, so if you'd like more information on that, you can visit my operator, or actually math parsing and evaluating in Swift tutorial. I have 2 of them. There will be 2 links in the description for them. Okay. Then what we're doing is we're calling the print legs function for ndisk, and then of course our 3 pegs, and then we're just waiting for input. Right as the input is given, meaning the enter button is clicked, this loop will iterate once more, and it will go through all of this. Now let me show you a demo for numbers 5 and numbers, you guessed it, 9. Okay. Okay, so now let me show you a demo for 5 disks. So if I type in 5, turn 0 of 31. So as you can see, as I click enter, 5 is progressively getting solved. We're on turn 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31. And as you can see, we have solved 5 disks. Now let me show you something really interesting. 9 disks. Seems crazy, right? Well, it is. So, as you can see, there are 511 turns for the number 9. That is a lot of turns for us to possibly go through. So now I'm going to show you something that's amazing. As you can see, it shows us 9 disks here. Now if I take the enter button and I just keep it clicked, like I don't release my finger, as you can see, you can watch the Tower of Hanoi get progressively solved. I'm going to stop at 100 here. And as you can see, on turn 100, we have already gotten to this sort of a state. We moved disk 3 from peg 1 to peg 3, and as you can see, we can actually see the entire history of all the pegs. We can see how each peg was moved. Now let's continue to 200. As you can see, it is getting solved quite nicely. And as I said, this is going to be, no matter what, like guaranteed to give you the lowest number of moves. It will never give you higher than what's required. So let me just show you quickly though. 511, so yeah, this is the minimum number of moves. You can't get better than this at this point. So as you can see, we are on turn 200, and we are moving disk 4 from peg 1 to peg 2. Okay, turn 200. Next, turn 300. And as you can see, we can see the Tower of Hanoi. If you can't see where I'm seeing this, just look at this specific board. Oh, I missed 300. But as you can see, now we're moving disk 4 from peg 3 to peg 1. We're just moving all of this, all of these disks and stuff until we get to the end where we have solved it. So actually, one thing that I haven't told you, this app isn't looking to complete the Tower of Hanoi. What it's actually just doing is it's just taking the instructions and following them one by one. It's not actually looking have we finished yet? If we have, then stop, or else look at the next instruction. It's just blindly following the instructions that it gets from the Hanoi node class, and so that Hanoi node class is guaranteed to give you the instructions that will work, and so that's why it can blindly trust the instructions from there. Now again, I'm going to click keep the enter button clicked. Now I'm just going to go straight to 511. Actually, I'll stop a little bit before there. Now if we just keep going, and as you can see, we are very, very close to having 9 disks in the Tower of Hanoi solved. And as you can see, last 2 moves. 2 goes on to peg 3, and 1 goes on to peg 3. Now, let me just show you. My UI isn't yet able to handle stuff like 10. This is due to the fact that, first of all, 10 has 2 digits, which completely messes up the pipe formatting, so that's one thing. Next, 10 has a 0 in it, and the 0 automatically gets removed, as you know, using our algorithm. So, I mean, I can fix that really easily by putting a symbol that you wouldn't really use in numbers, like a tilde or something like that. But again, then we'd have to redo the pipe formatting, and so it's just really hard. So till now, it's only able to do single-digit numbers, so from 1 to 9. Though you wouldn't really want to do 1, so from 3 to 9 it'll handle. So even though the instruction function can get for like even 100 disks if you were to give it enough time, but it can. So this UI can only solve the number of disks up to 9. That's it. That's the final thing. But really note, so one last note, just so you don't forget this, the algorithm can solve any number of disks as long as your memory permits. So final note, the algorithm can solve anything, the UI, that's lacking behind. But I'm planning on releasing, maybe, if I get enough views or ratings on this video or requests for it, I will make this UI better, and I may just include the double-digit, or actually any digit version of the GUI, or CUI. And that's going to be it for this tutorial. If you enjoyed, please leave a like down below. You can also comment down below, contact me on tadjimani@gmail.com or at tadjimani on Twitter. If you have any questions, suggestions, concerns, app ideas, anything really, you can just contact me on any of those 3 places. You can also send me a video question, and I might just feature it in one of my next videos. And you can also subscribe to my channel if you're new or you like my content, you want to see more of it. Really does help. And that's going to be it for this tutorial. Goodbye.